Welcome back everybody to class. When we left off, we had taken a look at some fundamental building blocks, specifically labels, identifying the fact that we can actually forward frames or packets based on these labels if we have two or more devices that are willing to go ahead and do it. We have taken a look at a lot of acronyms so far, and we are going to basically now dive in and make sure that we are comfortable with what those acronyms represent, because we will be using them more and more and more. So let's start off with the term of a LSR, a label switch router. All that is a device that is enabled with MPLS that understands how to forward with labels. That's it. So an LSR is very likely an IP router as well as an LSR, meaning it can forward on labels. Here's how it works. If I'm an LSR, a label switching router, and I have MPLS enabled on all interfaces, if I receive a packet and that packet has a label, I'm going to forward it based on that label. So I'll look up in my label forwarding information base, identify who the next hop is, what label I should push on it, and I'm going to make that forwarding decision. If I'm an ingress LSR, an ingress LSR is at the edge of our MPLS network. In fact, let's go over to our drawings and take a look at it right there. Let me bring you over there with me right now. And let me bring up this one. And here we go. Again, the controls in the bottom left will be able to identify and set up the screen so you can see it in the best possible light. So an LSR would be like a P router, a provider router. An ingress LSR would be considered a PE where the traffic is first coming into the network. Let's take a look at that in our drawing. So here in our beautiful MPLS topology that we'll be working with, and clean this up just a little bit. So as traffic comes in from this client up to the PE, that traffic is simply IP traffic. So we're talking about transit traffic here. So somebody at site B1 wants to ping maybe somebody over at site B3, or they want to go to, let me get my colors straight here. I want to use the same colors. So we'll use green for all that. So maybe somebody in site B1 wants to get to something at site B3, or they want to get to something at site B2 based on the destination IP address. As the transit traffic hits the PE2 router, it basically is going to identify whether or not there's labels associated with that destination. If so, it's going to impose or push on a label and forward it. In this case, it would forward it to this router here, which would be an LSR, a label switching router. It would say, oh, this label is coming in, I know what the outgoing label is. He would swap it and forward it to PE3, who would then strip off all remaining labels and forward as a naked packet down to B2. So that's how the ingress and the egress and the intermediate label switching routers operate. So does it mean if I say LSR that I'm talking about only a device that has MPLS on both sides? No. Any device that is forwarding traffic based on labels could be considered an LSR. Any device that's on the edge of the MPLS network, and between a normal IP network that's either imposing or popping off labels, that would be considered a provider edge router. So those are those terms, easy enough. Now, one of the other things that we talked about earlier, I want to focus on a little bit more right now, is the concept of upstream and downstream. What is that all about? Well, downstream is the actual network that you're trying to reach. Think of transit traffic as a river or a stream. It's always flowing down towards the destination network. So as far as who is downstream, who is upstream, it depends on the actual route that we're tracking. So if we go back to our diagram right here and take a look at it, let's focus on a route. If we're focused on this route right here, the 203.2.0.1 network that is owned by B1, the PE2 router would be the downstream router. He's closest from a MPLS perspective. He's closest to that network, and he would be forwarding the information upstream regarding it. So we forward control information, for example, labels, reachability, and so forth. The control plane is built upstream, away from the actual network, because people who are already connected, they know, right? And then transit traffic, I'll put that in blue. Transit traffic would go downstream. So the control plane is actually built upstream from the source of the network further away, and the transit traffic is going to be downstream towards the actual network itself. Those are important to know, because as you're reading documentation or working on a scenario and it talks about the upstream router or the downstream router, just think in your mind, okay, downstream means closest to the actual network, upstream means furthest away, and then you'll be good to go. Additional terms that we absolutely need to come to terms with, besides upstream and downstream, is we should also be aware of something called the control plane. Now this is a remote control plane, which is not exactly what they had in mind. But the control plane is how we train our network to forward packets, whether it's an MPLS control plane advertising labels, whether it's a IP routing control plane like RIP or EIGRP or OSPF advertising actual routes. The control plane is how your network learns how to forward traffic. So just be aware of the pieces involved. I want to focus for a moment on the MPLS control plane. The MPLS control plane is all about labels and sharing those labels with other people. The LIB, the label information base, is what your router is going to collect as far as local labels that it's generated labels for, and also labels that it's learned from others. So the label information base is all the information about all the labels for all the devices. So let's go ahead and take a look. I should say all the labels that our next door LDP neighbors know for all those networks. Let's go here. Let's jump back and let's go to our warm-up network. And our warm-up network is right here. And let's just go take a peek at the labels that R4 is retaining, that he knows about. And then we'll build from that. We'll take a look at the control plane and some of the other data structures that are present. So let's hop over to R4. And here's R4 right there. And let's do a show MPLS LDP, just show LDP, show MPLS, I just can't type, MPLS bindings. My brain. LDP bindings. Alright, show MPLS LDP bindings is going to show us all the current bindings on this specific router. So it's going to consider itself first. So take a look at this. It has, am I ready? It's got the 333 network. It's got a local tag for it. Let me get a different pen out. It's got a local tag for it right here of 20. It also has learned information regarding that 333 network from label perspective. It's learned that 5555, which is the LSR router ID, also happens to be the highest IP address of any loopback, that the label it's advertising is 24, and the label that 333 is advertising is implicit null, which is a fancy way of saying the reserved label of label number 3. Down here, we have another network, the 4 network. In this case, the 4 network is, I'm using a tag of implicit null, which is label 3, and I'm advertising that to my neighbors as well. And my neighbors are advertising, check this out, my neighbors are advertising to me. See, this is router 4, that's my local loopback. That's why I have an implicit null for it, because I'm directly connected. I have two neighbors that are advertising to me saying they can reach it if they need to. So basically, router 3 is saying it's using tag 22 for that network, and router 5 is saying he's using tag 25. I'm not going to use either one of those because it's directly connected, but if I need to, I'll have that in memory. And this is called liberal retention. Basically, we're going to remember and keep in our label information base all the labels that are shared with us and advertised to us. So if we have a fault or a failure in the network, it's sort of like a feasible successor with EAGRP. We can go to that backup path and boom, we're on the way. So let's do a little experiment with this one right here. Here's the 5 network, and R4 for the 5 network says that my local tag is 21, and I have 2 people that are advertising routes to me. Now, the guy advertising the implicit null, he is probably the best path because he's claiming to own that route. But let's say that this was just 27 and 3, and we didn't know because of the implicit null that this is the best path to go. How do we know? How does router 4 know to forward it to, to neighbor 333 with tag 27 or neighbor 555? Because check this out. If we do a show MPLS forwarding table, and we'll do it just for 5.5.5.0, 24-bit mask. If we look at just that one specific route, even though we had 2 people who said they could do it, we are using 10.1.45.5 as the next hop, which means we're going to pop the tag off because he advertised it to us as an implicit null, meaning it's local. As a courtesy, if somebody advertises an implicit null, we pop the tag off so he doesn't have to bother looking at it and say, oh, it's me, popping the tag off and doing an IP lookup. So we're saving him a step. So how exactly did he know, R4 know, that R5 was the best next hop? It's all based on the IP routing table. The routing table is the critical element that everything else is being built on. I mean, label distribution is simply, using the intelligence of your IGPs and figuring out the routing based on what your current routing table is. If your routing table changes, so will your LSPs, your label switching paths through the network. So let's do this. Let's do a show MPLS neighbor. No, MPLS LDP neighbor. Because you could have a TDP neighbor as well. There's 2 different protocols we'll talk about a little bit later. All right, so here we have 2 networks. The question was, why did we choose 5.5.5? Let's do a show IP route or 6. So here's why we chose R5. If we look at the routing table shows for the 666 network, the next best hop is 10.1.45.5. From an LDP perspective, we take a look at the neighbor who owns that next hop address, which happens to be this guy right here. And this LDP neighbor has the next hop of 10.1.45.5. That, my friends, is what makes him the best path for label switching. So it's reverse engineered, if you will, from the actual routing table itself. And that's how those pieces fall together. We're going to cover a lot more of this in a lot more detail, but I wanted to show you, there's no magic to it. It's just a matter of identifying the next hop from the routing table, which LDP neighbor has the next hop, and that's how you make the forwarding decision of what the next hop, if you will, is going to be from an MPLS label perspective. All right, so let's take a look at a review of those concepts we just covered. For MPLS, the control plane, we have the label information database. And the label information base is all the information on all the labels. Our local labels plus any advertisements we've received. If we look at the diagram again, R4 received labels this way and this way for the 5.5.5 network. And with liberal retention mode, R4 remembers all those labels. To make a decision on which way to go when he needs to forward to that destination network, he's going to use, based on the routing table, the best next hop, and whichever neighbor owns that best next hop, that's the LDP neighbor we're going to use. Now that seems like a lot of work. I know, it does. I get it. But because it's all done beforehand, it doesn't have to wait till a transit packet shows up to actually go ahead and make all those calculations. Once a route is advertised, it gets a label. It's then determined which is the best next hop based on a layer 3 routing table perspective and the LDP neighbors involved. And then that's all put in the adjacency table and the CEF table, so your router is ready to go. It doesn't have to figure all that out at the last minute. It's all pre-planned, which is a beautiful thing. The LDP is how we share labels with our neighbors. We have a whole module coming up on that. The label information base, as I mentioned, is all the labels involved. The actual FIB is the forwarding plane for CEF, and if you must know, CEF also includes the label information. So if we went and peeked at CEF on that same router for that same network of for example, 6666, and did a show IP CEF for that network, it's going to have in the CEF table, which is the IP forwarding table, it's got the tags that it needs ready to go. So the decision to make the forwarding, let's take a look at the tag here. Oh, I'm looking at a different network. Here I looked at the 555 network, now I'm looking at the 6. Let's go for the 555 network. Apples to apples. Okay, so in the CEF table, see here it says tags imposed, nothing, and that's because we're popping off the tag for that neighbor. But all that information is cached inside the CEF table. I shouldn't say cached, in the CEF tables, so that when packets come along, there's no decision process. We just fire and go and move on to the next packet. So the FIB, even though it's primarily for IP, we're also inside that CEF table for the forwarding information base. We also include the tags that we've learned from the label forwarding information base, which is next. And the LFIB is the winner circle. Just like a show IP route is the winner circle for how you're going to do your routing on your network, the LFIB is the winner circle for how we're going to be forwarding packets based on labels. So if we went back to R4 again, and on R4 we'd said, I have it in my cache, we did a show the bindings for, let's do for 5, and it wants 24 bits. Okay, so there's all the bindings we have for 5, and here's the winner circle for 5. And that's the difference between the two. So for routing IP, the RIB is like your routing information base. The FIB is how we're actually forwarding traffic with MPLS bindings. The LIB is everything we have. That would be this guy right here. And the actual forwarding, which one we're going to choose, the winner would be in the MPLS forwarding table, or the LFIB. And that's right here. And that's how those pieces fit together. So let's take a look at a review of these pieces, make sure we're all comfortable with them. So the IP routing table is the routing information base for IP, and the RIB information goes into the CEF table, which also there's an adjacency table, all pre-calculated so that forwarding can be extremely fast, and CEF and FIB make all that happen for IP. FIB also is incorporating the labels from the LDP process. So LDP is sharing labels with others. Every label is put into the label information base on the local router, and then the winner, the best possible path, which is also tied back to the RIB table, is placed in the LFIB as far as the best destination or the best path based on the routing table. So the FIB you can kind of think of as for IP and a little bit of MPLS, and the LFIB is specifically just MPLS, the winner circle for forwarding traffic. We also took a look at a couple reviews of those concepts at the command line. So here's a show IP route showing the routing information base. If you'll notice on the left-hand side, these are IS routes. A lot of times people are familiar with OSPF and EAGRP and RIP, and perhaps ISIS not too much. In our service provider network, we're going to use ISIS. We could use OSPF as well. In fact, we could use other protocols, but for traffic engineering, which is one of our last modules of the course, we are going to need some very intelligent link state information from ISIS or OSPF. So instead of swapping it all out the back end, I'm simply using it up front. The CEF table is the Cisco Express Forwarding table, and again, that's primarily for IP. However, we are injecting the actual tags as well so that we can be ready to forward traffic, whether it's tagged with MPLS frames or MPLS headers or whether it's straight naked IP. So if we go here, and let me get my slides all lined up. So here's LIB and CEF for one specific network. As a nice recap, we did all this live, but the routing table for 192.168.3.4, and then down below we have the CEF entry for it, and you'll notice we have tags as part of that. But more importantly, we have the next hop all figured out and the exit interface. And from the adjacency table, also maintained by CEF, it will go ahead and figure out the layer 2 encapsulation and so forth that's required. Here's the label information base, again as a review. So that has all the labels, good and bad. Implicit null is, if somebody is telling us about an implicit null, advertising it to us, that means that they want us to pull that top label off, and we'll be happy to do it for them. So if we're forwarding to and we've been told by a neighbor implicit null, we're going to pop off that top label and hand it over to them. Here's the winner circle. So previously, that's all the bindings, and the winner circle is simply the ones that we're going to choose. And again, how that works is we'll take the actual route we're trying to get to. We'll take a look at the routing table next hop, and we'll determine which of our LDP neighbors has that next hop, and that will be the best neighbor that we're going to use for label forwarding. And hence the label forwarding information base is born. And here's a recap of the LIB and LFIB for one specific route. I think it's important for us to see them so that we make sure that people know exactly what is there. So here's the LIB and the LFIB for 192.168.3.4. At the top, it's showing you the bindings, and at the bottom, it's showing you the winner. Now there's only one neighbor advertising a tag for it, so that's neither here nor there, but that's how it operates. All right. Okay, so we've covered a lot of basics with MPLS, a lot of building blocks. I know we've talked about labels, we've discussed them, but I've got something really cool to share with you when we return, and that is the actual details of the label, what goes in them, where they fit exactly, and also the possibility of having multiple labels. All that and more when we return.